Right, should we get started? Well, welcome back everyone. Before we get started, I'll just, so yesterday I set an exercise of just taking, say, ground state of 12 sites of a spin half Heisenberg model and just cutting it into two pieces. Keeping some truncated rank, say sigma equals 2, 4, or 10 values. So this type of thing, this is just an example, like if you are new to this area and you want to get into tensor networks before you start programming, trying to program an algorithm, programming DMRG, just try to do something like this where you sort of first understand how to pull tensors apart, how to manipulate them, how to put them back together. So something like this is a very good exercise, and it's also sort of very illustrative to how powerful tensor networks are. So even with a small bond dimension, you get about 6% error, goes down to less than 1% error. Once I've gone up to bond dimension 4, goes down to 0.1% error in the energy of the ground state. So you can sort of, in a simple example, sort of convince yourself, oh, this is these tensor network decompositions are very useful in practice. They're not just some sort of theoretical nicety. But today's talk will be on real space renormalization group and tensor networks. In particular, getting to this concept of entanglement renormalization and the multi-scale entanglement renormalization ansatz, the MERA. Okay, so the underlying theoretical framework of this is this concept of real space renormalization, also sometimes called coarse-graining, or I'll use that term interchangeably here. And so this is sort of a very general principle. So imagine I have some theory, some microscopic description of some theory, so very many spins on a lattice. The size of the problem, the Hilbert space, is far too big for me to solve exactly. So what I can try and do is somehow derive an effective theory with some sort of reduced number of degrees of freedom, so very many microscopic degrees of freedom, and now I want to sort of identify and isolate a few sort of effective degrees of freedom that are relevant for describing my problem. And so we're going to start off with a lattice in real space and go to sort of a coarser lattice. How we do it, and you may have seen like pictures like this, where so I have some, I'm going to have some fixed points, okay. So let's just say H ord, H disord, and H critical. So you can imagine this RG flow as generating some flow, and say, I'm imagining this is some couplings, this is some parameter space of Hamiltonians, maybe some couplings. You can imagine I start with some initial Hamiltonian, let's say H naught, and in the RG flow, so H1, H2, I should eventually flow to some fixed point. So let's draw here. So I'm imagining maybe this is many steps where I first generate some sequence of Hamiltonians. Okay. So depending on like where I start in this parameter space, what I hope is that I should try and endeavor to implement my renormalization in such a way that is consistent with this picture where I want to flow to the correct fixed point. So an example of this is if I started with the icing model, 1D icing model in a transverse field. If I start with some magnetic field below the critical magnetic field. So all of these Hamiltonians below the critical field should all flow to some ordered fixed point under this RG. All the Hamiltonians above the critical field should flow to some disordered fixed point. At criticality, I should have some scale invariant, highly non-trivial fixed point. Okay, so this is sort of a key. This is what we want in defining an RG flow. Is that proper RG fixed points. We also want sustainability. Okay, so we want to be able to, for some model I'm interested in, be able to actually implement this efficiently and not have it become too computationally expensive, not have it break down. We also want to preserve locality. Okay, and what we'll see is that these things are not necessarily as simple as you may imagine them to be. So this was really the problem Giffray solved when he introduced this entanglement renormalization, and this MERA was figuring out how to do real space renormalization in a way that gives us the expected properties. And this idea of these coarse-graining for classical partition functions and path integrals, this tensor network renormalization that Naoki mentioned in his talk, this is essentially the very similar ideas, generalizations of ideas from the setting of quantum systems on the lattice to classical systems to path integrals. Okay, let's get started. Okay, so let's do some coarse-graining. Sorry. So CG. So our first attempt is going to just be the simplest thing you can imagine, is some kind of real space blocking. So imagine I have a 1D lattice of sites. It doesn't have to tie them with anything in particular, but you can think about spins if that makes it easier. So this is a lattice L0. Maybe we have some Hamiltonian H0 on this lattice. What we want to do is figure out how we can do some real space RG on this lattice. So the simplest way we could do this is to divide L0 into blocks. Here I'm going to do blocks of size 3 though, because this will be convenient for later, but in particular any size blocks would work. So we're going to coarse-grain blocks with an isometry called W0. Okay, so if each of these sites down here is described by some Hilbert space V of dimension chi0, then this isometry W0 is just a mapping from taking me from V of some new dimension chi1, or actually taking from 3 sites of my original lattice chi0 to one side of my new lattice of dimension chi1. So we know we could draw W0 like this. Okay, and what we have, so we're imagining this output is mapping to some new lattice L1 like this. Okay, and so W0 as an isometry, it has particular property that W dagger W equals identity on I1. So graphically we would draw this as W with its conjugate equals identity. Okay, and we're going to, let's say, we're going to call big W as just the tensor product so the big W is a tensor product of all of these local transformations. So here we're associating this big W as a mapping between our initial lattice and our coarser lattice. Okay, so this is just the simplest thing we can do. So question, does this preserve locality? And so here, this property of it being an isometric mapping is very important, and that we'll see, yes, this transformation does indeed preserve locality. So how do two-site operators map? Okay, so imagine I just have some local operator on this lattice. I want to figure out how this maps to my new lattice. So we're looking at big W dagger acting on some local operator O. So we get so imagine our local operator is here. Then we have the conjugate. Okay, so these isometries extend off onto either side, the whole lattice, but you can see W dagger cancels out, so this just equals a bunch of identities. A new operator we'll call O prime. Actually, let's call this O naught, and we'll call this O1 with identity. Okay, so here O1 equals O naught acting with these isometries in this way. Okay, so all of you should be well familiar with this notation by now. If I gave you this operator and this isometry W, you should be able to figure out how to do this efficiently numerically. So this is no big mystery. This is something we can easily do, and we'll see. Oh, this two-side operator has mapped. Oh, this two-side operator is mapped to a new two-side operator under this coarse-graining. The exact mapping depends on where this operator sits on the lattice in relation to these isometries. So we have other, so sometimes O1 could be a one-side operator if it sits, for instance, directly under one of these isometries. Okay, but the important part is it doesn't delocalize too much, it doesn't spread out, it either stays a two-side operator or it maps to a one-side operator, and it will keep mapping in this way. So yes, this sort of very basic transformation we have sort of ticks off the box of fulfilling, preserving locality. So we can imagine, let's see this. So let's set aside the problem for now of how we actually choose this W naught. We'll come back to that, but let's imagine, so we have our H naught sitting on our lattice L naught. Oh, and so of course, before we do that, let's go up here. How does a local Hamiltonian map? So if I have W dagger H acting on W dagger acting on a Hamiltonian, that equals a sum over some local terms. So let's just say 2 site. Well, of course, the Hamiltonian maps as it's just a sum of local operators, so it becomes a new sum of coarser operators. So we can actually, so this equals some new Hamiltonian H1. We know H1 is the sum over some new couplings H1 that are at most 2 side again. So we can draw the new coupling will just be the sum of some terms like this, with an extra 1 as well. Okay, so this, if I gave you the sequence of W's, you could interpret this as a transformation that you could use to map your initial Hamiltonian to some new Hamiltonian. So we'll say this lattice L naught has N naught sites, chi naught dimension. Okay, so each maybe is a 2-level system or a 4-level system, it doesn't really matter. Okay, and we have some mapping to some new lattice L1. This new lattice is N naught over 3 sites, chi 1 dimension. Okay, so maybe I've increased the number of degrees of freedom. I keep, so at the moment this is the dimension of each site relates to my, I'm going to call chi, which relates to a bond dimension of this isometry. Okay, so this is the idea. Eventually we want to keep going until we reach some HT of LT. Okay, so here we want order 1 sites, and we'll have some T dimension. Okay, so here T is of order log 3 of my N naught. Okay, so I want to be able to keep doing this transformation until I get to a lattice of order 1 sites. So do it a logarithmic number of times. Let's just draw a little bit more here. Okay, so imagine I've reached a small finite lattice. So once I get to this HT on my small lattice, I could just diagonalize HT. For its ground state, let's call it phi T GS. Okay. Let's actually put it, let's imagine this is our small lattice. Let's put it here, phi T, phi GST. Okay, so this L2 here is now a 2-site lattice. We've gone all the way to here. We've put our state in. So the first thing we should realize is that so this W0, W1, WT acting on phi GST equals, let's call this phi GS naught. So this is some quantum state on L naught. So this this state on the most coarse level of the lattice in conjunction with these RG transformations, we can think of these things together as they define a state on my initial lattice. This is precisely my so this is precisely this big tensor network state I've drawn here, which is a tree tensor network TTN. Okay, so we started off thinking about each of these layers as implementing an RG transformation in for a quantum lattice. When we put these different RG transformations together, we interpret it as describing a tensor network ansatz. Okay, so hope you appreciate this point. I don't think it's obvious, but it's certainly very useful. Is that so I've tried to explain a link between this idea of renormalization, rescaling transformations, and certain types of tensor networks. So this is actually a very useful way of thinking about many tensor networks, and actually this is how you compute things with tree tensor networks and with MERA. So forth. Okay.
By the way, is this the title of Masaki's talk?
Oh yeah, sorry, I just uploaded that, so you can read it. Sorry.
I see. And what does it mean? Today real space renormalization?
Oh, this talk. Sorry,
Masaki drew that.
I see.
Sorry,
That's fine. Okay, so this is the concept of what we're trying to do. So now we should answer the question, how well can this work? Or equivalently, how to choose this set of transformations, let's say WZ. Okay. Okay, so maybe, so I mean, of course there are, in practice we're going to do some variational calculations to optimize this network, but at the moment we just want to understand conceptually what this W0 should be doing, how big do I need to keep this bond dimension to represent certain types of state. Okay, this question of how you do RG, real space RG optimally was solved by White when he, in the formulation of DMRG, and that, so W0 should preserve support of the density matrix. So I think this is a very important point. Before White came up with DMRG, people were trying to do real space RG. What they would do is try and choose this coarse-graining transformation, for instance, to project onto the part of the block Hamiltonian that had lowest energy. This often didn't work very well, which was why prior to DMRG, real space RG had a bad reputation as just not being very good. Like momentum space RG was great, real space RG is not very good. Until White came up with the idea of how these should be better chosen. So the idea, so let's just imagine we have our lattice L0. So this is L0 with my Hamiltonian H0. Let's just imagine we have the exact ground state phi exact ds has this tensor. So my problem I want to do is I want to find some W naught to try and coarse grain the state that we're assuming we have. How should this W naught be chosen? Well, let us consider, just call this block A. Let us consider row A as the reduced density for a block. If row A has an eigendecomposition, sum over J, Vj, lambda J, Vj, dagger, where I've ordered my eigenvalues in descending magnitude, lambda 3, then W naught should be chosen as the span of the dominant eigenvectors. So V1, V2, V whatever chi I'm using. Okay, so here row A is of dim some chi naught cubed. So the optimal choice of this W, as argued by Steve White, was I should choose this isometry as the span of the dominant eigenvectors of this density matrix. If I knew them, this would be sort of the optimal I can do for whatever bond dimension I'm using in terms of this is what the RG should do. It should preserve the ground state. Or maybe the ground state subspace, or maybe some sort of subspace containing excited states, if those are what I'm interested in as well. But for the ground state, this is the optimal choice.
In what sense it is optimal? Are you going to talk about that? I can vaguely guess why it is, but to be more...
Well, it's kind of almost by what I would say is definition, is it's the choice that preserves as much of the ground state as possible. So
I think that for a given number of chi y, it's an optimal choice.
in the sense that we can imagine, so you can imagine after this transformation, this thing is representing some coarse-grained state, then this choice will make sure I've preserved as much as this is possible. So the norm of this guy with itself will be some value less than 1 relating to the eigenvalues I've truncated. This choice maximizes this norm. So somehow if we're only, under this choice, we're only removing degrees of freedom that don't play a role in the ground state or play as minimal role as possible. Okay, so this so now this is very useful. So we've understood the optimal choice. How well this choice works for a given dimension relates to now how quickly the eigenvalues of this density matrix are decaying. So so we have some chi naught to chi 1 to chi 2, chi 3, etc. So how big is chi z? And again, this now relates to a question of entanglement that we can at least address the scaling in some very generic way. Okay, So what we should notice is that a site in lattice LZ equals 3 to the power of z minus 1 sites in L0. Okay, so a site up here, if I take it down to the initial lattice, it's 9 sites. A site up here is 3 sites. Okay, so we can understand how big this site needs to be, the dimension of this site, by looking at the entanglement entropy scaling in systems. Let's actually go straight to looking at the case of a 1D critical system. So I can just, well, for a gap system, this ansatz is very similar to a matrix product states in a lot of ways. The answer, without going through the derivation, is, oh, because entanglement saturates at an area law, then this dimension can be finite. In a critical system, I have so my entanglement entropy scales as S of L, going as log L. So we have a logarithmic correction to the area law. What this implies is that so S is polynomial in Z for a single site. Okay, so as so a site in lattice, so each time I go to a higher scale, I'm exponentially increasing the size of my block, but the entanglement entropy scales logarithmically in the size of my block. So the combination of exponential scaling of the size versus logarithmic scaling of entropy gives us this polynomial for site in LZ. Okay, so entanglement entropy of single sites is increasing polynomially. What this implies, of course, so my dimension at level Z should scale exponentially with Z. So as we saw yesterday, the effective dimension needed to represent some amount of entanglement is exponential, and whatever that entanglement is.
So, if you do critical systems with matrix product states, you don't need an exponential quantum dimension. It just sort of makes it a little more costly, and if you increase the system size, it sort of is, I don't know.
No, so here, the reason this is exponential is we're talking about the bond dimension at different scales. So this is
so it's for a tree in particular.
So if we want to be able to do 2 RG transformations, we need exponential in the number of RG steps, but the system size is also growing exponentially in the number of RG steps. So so here the cost is growing exponentially in Z, but the system size is exponential in the number of layers Z. In matrix product states, the cost is polynomial in the system size as well. So this would also translate into cost polynomial in the system size,
Yeah.
but exponentially expensive if we measure it in the number of RG steps we want to do. Okay. So what I would say here is that this is represents some kind of breakdown in the RG flow at criticality. So breakdown, so this is a very bad thing. This is, I would say, so had with we're talking about tree tensor network. So we saw this has the property of preserving locality. These two properties are not don't happen with this simple ansatz. So sustainability, it's not sustainable because I need exponentially large bond dimension in order to realize this RG flow, so I go a little bit, then I have to stop. If I'm at criticality, you don't get proper RG fixed points in the sense that I find here. I saw as if I started a critical system, things are getting exponentially expensive as I coarse grain. Clearly it's not going to a fixed point in that sense because something is exponentially diverging. It's not the same theory in this sense. Okay, so this is it's a practical issue, it's a numerical issue, it's also a conceptual issue as well. So these are the things we want to try and address. Okay, so any questions at this point? Nope. So the origin of where this is coming from, you can imagine. So if I had some theory down here, if I had some state down here, if I had some short range entanglement, you can see that this isometry can sort of absorb and remove this. So some short range entanglement or short range degrees of freedom, this transformation works very well if it's under the isometry, but you can clearly see that across the boundaries of blocks, if I have some correlations between these spins, they become correlations between these coarser spins. So this is sort of the root cause of these issues, is that some entanglement propagates. Okay, and this, and so this is the key issue. How do we sort of fix this problem at the same time without delocalizing things too much? So we can't just, so I mean the simplest thing you could try and think of is, well, maybe if I have some kind of transformation that doesn't have this block structure, then it could get all the entanglement, but you also are constrained by preserving locality. Okay, so let's do and so this was so new RG attempt, entanglement renormalization. Okay. So again, my local lattice L naught, my Hamiltonian H naught. So as before, I'm going to divide into blocks. Again, so 3-side blocks for simplicity, though any number of sides may do. Here's the key step that sort of fixes the problems we saw before. Disentangle between blocks. Okay, so I'm going to introduce some unitary matrix U that now straddles across the boundary of each block. Like that. So this, again, each of these sites is described by some privilege space V of pi naught. And what this is doing, so U naught is some mapping between filter space chi naught squared chi naught squared. And it's a unitary mapping, so u dagger u equals u dagger equals identity on chi naught squared. So graphically we would draw this as u dagger equals 2 copies of the identity. Okay, and so our third step is just block is the same as we had before, it's just to put the isometries back in. Okay, so again, just like we had before. And this is our mapping to some ortholattice L1. Okay, how do local operators map? So these disentanglers, they spread out in directions. So now if I have a two-side operator here, this guy spreads it out, so it now becomes an operator on 3 sides. But then these disentanglers sort of compress things back down. What we can see is that two-side map to two-side operators. Okay, so let's call this whole layer some capital V. Then if we want to understand how VDAG H0 V maps, so it equals some H1 is the sum over some local couplings, H1 R plus 1. What do these local couplings look like? So we just do an analogous calculation to what we showed you before. H1. So a new two-body coupling down here. So some H1 is going to come from the sum of 3 two-side couplings H0 down here. So all of these under this coarse graining will only involve 2 sides up here. So I define my effective coupling as the sum of 3 coarse grain couplings. So this looks like H0 U dagger W dagger plus the one coming from, okay, so this one is the one from the middle sitting under the disentangler, and then I have one more on the right, which very quickly okay, and as so this is the definition I use to generate my effective coupling. This diagram I actually used in one of the examples yesterday when I was describing how to do tensor networks. This was the one that we had to figure out that was chi8 in contraction cost. So again, these may look very scary, but once you have some some codes and formalism for dealing with tensor networks, then these are certainly not so bad. You can evaluate this pretty easily. Okay, so we had our H naught on L naught. We now have a mapping so forth. Okay, and this mapping is implemented by some disentanglers and some isometries. So again, I haven't told you how to find these things yet. Okay, so some sequence of coarse-graining transformations would look like this. Again, what we can say so if phi t ds is some state we get from diagonalizing h of t, then phi naught gs defined as v naught v1 vt acting on this guy. Okay, so sequence of RG transforms plus our course of state equals a MERA. Okay, so again, so when we interpret these as not just an RG transformation but as part of a network, then this structure of these disentanglers and these isometries is precisely a MERA. In this case, we call this one a ternary MERA. Ternary meaning 3 because this takes 3 sides to 1 with each coarse graining. So of course there are many different ways, many different forms of MERA you can do. This one is particularly convenient because 2-side operators map to 2-side operators. Other forms of MERA may have different degrees of locality. The binary MERA, you have 2-side operators mapped to 3-side operators, but then it stays at 3. But in order to be a MERA, you have to have some kind of maximum spreading of operators under this coarse graining, so you have to preserve this locality to some degree. Okay, so RG transformations equal tensor networks in this case. How well does this work? Again, what I can say. So now so there aren't a huge amount of conceptual derivations you can do with the MERA. So what we can argue theoretically is that this MERA doesn't have the same problem we encountered before. So if I have some short-range entanglement, if there's some short-range entanglement here, it can be taken care of by this isometry. These disentanglers here take care of the stuff that was missing before. So you can make some argument that this should be a good ansatz. There is not a lot more you can do beyond this sort of arguing, but what we find in practice is that so fixed bond dimension works. So we can show that you can do very many of these RG steps, will still give me very accurate results with some overall fixed bond dimension. We can show that fixed points are reached as well. Okay, so as an example I said at the start of the talk, if I have, say, an IC model and transverse field, if I start at the Hamiltonian anywhere below the critical field, I will go to some very simple Hamiltonian that describes an ordered fixed point. It's the same Hamiltonian no matter where I start. If I start above the critical field strength, I'll go to some other different Hamiltonian describing the disordered fixed point. If I go to, if I start at criticality, I will have some scale invariant Hamiltonian appear at each RG step. Okay, so MERA, we find when we do this, we get all of these things. In particular, we get scale invariance for critical systems. Okay, so what this allows us to do, so a scale invariant MERA, we can, if I was doing it in the notation I used here, so scale invariant MERA could be described by some fixed RG transformation infinitely many times, maybe with some initial transition layers. Okay, so this is again an observation numerically. If I put an Ising Hamiltonian down here and I try and do this coarse graining in an optimal way, I find after some initial layer that all of my layers can be chosen in the same way, and this gives me a good approximation to the ground state. And sort of this is certainly not obvious a priori. Okay, let me just summarize. Okay, so what we've seen so far is some kind of transformation for a lattice just based upon blocking equals a tree tensor network. Okay, so RG transformation can be interpreted as a particular class of tensor network. This works in a very similar way to matrix product states, or it's roughly very equivalent. But if we want to interpret this as an RG transformation, we want to implement this for critical systems, there are some problems with this. So we have this other way of doing lattice coarse-graining transformations called entanglement renormalization. This is the sort of theoretical underpinning of a MERA. I'm not going to draw again. This guy. And this was specifically designed to address the problems that tree tensor networks have while still having this important real space criteria of preserving locality. So this tree tensor network is good for numerically 1D gapped, 2D not so much, so gapped or critical, 1D gapped thick. (2D) gapped or critical is going to be exponential, doubly exponential, the bond dimension size and the number of RG steps. This supports the 1D area law. S about goes as a constant, doesn't support 2D area law at all, whereas this MERA, we argued, it naturally reproduces logarithmic corrections to the area law in 1D. The 2D, MERA reproduces the 2D area law, and in practice we find it's good for a number of 2D systems. If we need a slightly upgraded MERA to do certain types of highly entangled 2D systems. So in 2D you can have systems where you have L, log L, L log L, you need something other than a MERA in order to make it work by the same arguments we had here. Okay. We all good so far? Questions? Yeah.
Could you explain how can we construct unitary U?
I wasn't going to go into the numerical side so much in this talk. So in practice, all of the techniques that work with standard tensor networks, variational principle, variational energy minimization, imaginary time evolution, these algorithms can be generalized to the MERA. So most of these algorithms, like energy minimization, the key part here is if you can evaluate the energy efficiently, then you can change the parameters in the tensors to minimize the energy to get a good approximation to the ground state. There are other ways of getting the MERA now, so we know through the coarse-graining of the path integral using tensor network renormalization, so something slightly different that Eriki talked about, we can also get to a MERA in a very different way. In my talk on Monday, I described for the case of free fermions how you could analytically derive unitaries and many examples based on some wavelet construction. So now at least there are some, there's a paper out you can look at that will give you some analytic idea of how this unitary can be constructed in at least some examples. Okay. So what is MERA good for? I thought I would it's really nice to explain what sort of two-point correlation functions MERA has.
May I?
Yep.
So can we implement the 2D MERA for the fermion system?
Yes, people have done that.
Because the fermion is not the local.
So there are very general ways people have figured out for implementing fermions with any tensor network. So you just have some bookkeeping to keep track of the fermionic sign. So with PEPs, with MERA, with any tensor network, we have some sort of general way of doing this. The main problem with 2D, which I was going to touch on later, is that just computationally the algorithm becomes much more difficult. So especially with MERA, to some degree with PEPs as well, you just have much more complicated diagrams you need to contract. It's much more expensive, but the actual dealing with the fermionic sign is not the problem at all. This is why why these are very promising for fermionic systems. It's precisely because of this. And this other network, the PEPs, is giving, at the moment, for some systems, the best results out of any numeric method. So you can certainly, then, because Monte Carlo can't even be applied in a lot of these cases. So let's look at correlators in MERA. What I'm drawing here is just a schematic representation of the MERA. So I'm imagining each of my layers here. So I have some scale invariant MERA defined by some sequence of identical layers called V star. So in here I'm just imagining I have my tensors, but I'm not going to draw them. And the question we want to look at is if I have two local operators that are some distance L sites apart. So let's call this whole thing just some phi. What is say O naught and so this is subscript with a bracket for the scale in this case. So what is my phi O naught? Okay, so what can I say about the 2-point correlators in a MERA without actually knowing any of the content of the tensors? What we expect from conformal field theory so conformal field theories, at least for two-dimensional classical or one-dimensional quantum, are very well understood conceptually. There's just a very nice mathematical framework, and what we expect is 2-point correlators, say phi alpha at some distance x, phi alpha at some distance x plus L, should scale as L to the minus 2 delta alpha. Okay, so here delta alpha are scaling dimensions, phi alpha are scaling operators. So the idea is that if I want to know any 2-point correlator between any operators, well, I have these things called scaling operators. Any operator can be realized as a linear combination of scaling operators. The scaling operators can be understood to have some exact polynomial decay in the correlators. So it should be a 2. So this is some exact polynomial decay I expect. And in particular, any CFT has a discrete spectrum of scaling dimensions. So a critical system, I have polynomial decay. There's not any polynomial decay. I only have powers. I only have a discrete set of powers. So for the Ising model, I have 1 over 8, 1 plus 1 over 8, etc. So there are only certain exponents of the polynomial decay for each CFT.
Can you connect this to the structure of the entanglement spectrum as well?
Yes, you can. You can. All of these things are related in some very nice way. So the spectrum of scaling dimensions relates to the spectrum of excitations if I put it on a finite system. It relates to the entanglement spectrum if I do a cut across the half system. All this relation comes from conformal symmetry. So yeah, like my freedom and sort of how I if it comes from. So here I'm thinking about a 1D quantum system where the other dimension is some imaginary time if I want. But this is equivalent to a 2D classical Ising model or 2D classical CFT where I have the freedom to change what I'm thinking of as space and imaginary time. This conformal symmetry gives all these nice relations.
Maybe just a follow-up question. So we know that in CFT, the entanglement, the modular Hamiltonian is related to the twist operator. So is that somehow clear in the MERA representation?
It's not exactly clear. We can maybe we can talk about this later so we have some understanding of how to think about the twist operators and how these things relate, but it is getting a bit more complicated. Okay, so the idea is, can we reproduce this expectation from conformal field theory? Simple expectation, does the MERA have correlators that scale in the same way? How we could do this, so imagine I have my local operators down here. What I showed you before is how we can implement a coarse graining of local operators in our MERA. So I could take these two operators, I could coarse grain them to some new operators, let's call them O1, living on my coarser lattice. So because I'm taking 3 sites into one with each coarse graining step, what's going to happen here is this. I now only have L over 3 sites between them in my coarser lattice. So here my for simplicity, I'm just going to assume, so let's say O1 equals S of O0. I'm going to call this the scaling super operator. What this is just the thing I drew before, which I'm just going to take one of the possible contributions, 3, so this is my operator, my unitary dagger. Okay, so this whole thing minus this local operator here is what we call S, the scaling super operator. What this does is it takes an operator O and it maps it to a new site operator, a new 2-site operator we're calling O1. So super operator as it's something that acts on operators, so acts on 2-site operators to give me new 2-site operators. Okay, and what's going to happen with this MERA is I can keep mapping my 2-site operators. Eventually they're going to be on nearest neighbor sites, so 0 sites in between. Once they get to nearest neighbor sites, I can just evaluate it as some constant that I don't care about. So the important part is that this merger happens at scale Z equals log 3 of L. Okay, so after log 3 steps, they will be on nearest neighbor sites. Okay, so my so x plus L. So my 2-point correlator is just going to equal the trace of the density matrix, so the density matrix on whatever sites they sit, versus my operators at this, sorry, I'll call this T, at this maximal scale T. Okay, so these are my coarse-grained operators. Okay, so how do these guys look? Well, in order to understand what these guys are, I should think about the eigenoperators of this transformation of this scaling superoperator. Okay, so consider eigenoperators of S. What I mean by this is we want S to act on something, we'll just enumerate them over alpha such that I get back the same operator with the coefficient. So, and what we can see is if we replace this operator by identity, then U and U dagger will cancel, W and W dagger will cancel. So identity will map to identity. So identity is one of the scaling operators, the trivial one, but there are many more. So let's consider a slightly simpler case than we had here. Let's consider in a MERA what happens if we evaluate two scaling operators, so one at position x, one at position x plus L. So as we saw before, in order to evaluate this, I should apply my scaling superoperator, log L times to this guy, log L times to this guy separately, and then I'll get something I can evaluate up to the constant. So this equals, each time I apply the scaling operator, the scaling superoperator to this guy, I get a factor of lambda alpha. I get a factor from each of these, so that becomes 2 times log 3L. And here I just have, my scaling operators come together on, say, neighboring sites. Okay, so this is after I've applied my operator S times. They come together. They're just going to give me some kind of constant. So this whole thing is just some constant. It doesn't depend on L at all. What I have here, so let's define delta alpha is equal to minus log 3 lambda for simplicity. When I put delta alpha in here, so my 2-point correlator equals, I do some algebra, it comes out as L to the minus 2 delta alpha, just times this overall constant that I don't care about, but the scaling, okay, so this is exactly polynomial scaling.
Are we assuming that exactly scaling invariant tensors are from bottom to top?
Yeah, I'm assuming we're in the scaling invariant regime, so yeah, each of these layers is the same. So even if you in the practice you may have some transitional layers, but this is just the large distance scaling. Okay, so MERA gives something consistent with CFT in some very nice way, where exactly we match the scaling operators and the scaling dimensions from CFT with the eigenoperators of the scaling superoperator and the log of their eigenvalues. So the calculation I've shown you here is actually one we do with MERA. So we optimize a MERA for a critical system. We diagonalize the scaling superoperator to extract these scaling dimensions in this way by just taking the log of them. So this is something very easy to do with MERA. If you try to do this with DMRG, with matrix product states, it's very difficult. Even if you can have a matrix product state that has a good representation of the ground state, you still have a very difficult time evaluating these operators from it. And the advantage from MERA comes in that you explicitly capture the scale invariant aspect of the state, and you have very nice access to the scale invariant data that describes the CFT. Okay, still got a little bit more time.
Excuse me. In general, lambda could be the complex, and how can we consider it here?
It could be. This is a good point. So this this guy is not Hermitian. Lambda could be complex in practical MERA calculations when we optimize a MERA. If our MERA is a good approximation to the ground state of a critical system, we find many of the lowest lambda are real and positive, which is good. So you get some of these guys very accurately with MERA, then some are very incorrect. They may have complex parts, so forth. You interpret these as sort of errors coming from the finite bond dimension. If one of the dominant eigenvalues is complex, you probably don't have a physical MERA, or maybe done something wrong at some point.
Another question. This phi alpha can it be a derivative operator? I mean derivative of some primary operator?
Yes. So here, according to the in a CFT, you have some operators which are considered the primary operators of the CFT, and you have their descendants, which are integer values larger than the derivatives of these primary operators.
Right. In that case, there are infinite number of eigenvalues, but on the other hand, we have only finite dimensional tensors.
Yes, this is a good point. So, yeah, there are in the exact CFT there are an infinite number of. If I consider this primary scaling operators, the scaling fields, and their descendants, there are an infinite number of descendants. We only have a finite dimension operator. Clearly, we cannot have all of them reproduced. In a MERA, we get some amount of them correct, which relates to the finite bond dimension we're using. The fact that there are an infinite number of operators is also a good argument for why a finite bond dimension MERA can never be exact. If you have finite bond dimension, you're never going to reproduce all of these things exactly. So unfortunately, for matrix product states, you can come up with exact solutions to certain models. With a MERA, this argument means very strongly that if we're not going to have a finite bond dimension MERA that's an exact representation of a critical system.
I have a question. There is a thorough scaling dimension in CFT. Such a condition can be introduced explicitly in a scaling super operators. Numerically, we obtain 1/8 and 1 plus 1/8 essentially. However, usually always such a structure in the scaling dimensions.
What's the question, sorry?
Yeah, if 1/8 is a scaling dimension, so 1 plus 1/8 exists in the thorough.
In the CFT, yes.
Can we include such a condition in the scaling superoperator explicitly?
It would be nice to understand more of this in practice. I don't know how to do this, or I don't think anyone does. Yeah, we really, numerically this works very well. I think conceptually a lot needs to be done in better understanding how these scaling dimensions come out and relate to content of these tensors. It would be very nice if we could have some restriction on these tensors that was a valid restriction for the CFT that ensured we were getting something correct, as you're saying, the descendants were appropriately spaced, so forth. Some of this work with wavelets I talked about on Monday, I think, is a step in that direction. So we have some analytic approximations. Many of the scaling dimensions come out exactly correct, and their descendants. So there is at least some avenue of possibly better understanding what's going on.
Yeah. In some ways, it's a bit surprising that you can construct these states which are scaling invariant, but not describable by a CFT because they have a finite structure of the descendants. So is there some feeling for sort of what goes wrong? Like what makes it not CFT?
No, this is a very good point. So before I answer that, like, we can make the analogy for matrix product states. Any matrix product state can be connected to the ground state of some gapped Hamiltonian. So you may think naively, oh, maybe any scale invariant MERA should be connected to the ground state of some critical Hamiltonian or something similar. Unfortunately, that's not the case. In some sense, MERA is over-complete in the sense that if I just randomly choose a scale invariant MERA, so I can just choose random tensors, make all the layers the same, the state I will end up with is very far from being translation invariant. So it's not translation invariant, but it's somehow critical. It's not related to a CFT. And we don't have any, again, we don't have any understanding. If anyone wants to solve this problem, I'd be very happy, of how to restrict these tensors to make the MERA scale invariant. It seems to be a very tough problem. Any more questions? So I thought I would take the final few minutes to just give you a simple example of a MERA we can write down that hopefully gives you some more intuition than just sort of these abstract diagrams. Am I able to move the whiteboard in front? It might be a little easier. That's good enough. Okay, so what we're going to think of, we're going to do a MERA. So thinking of a MERA, I'm going to think of bond dimension chi equals 4. So each of these lines of the MERA can be thought of as a product of two smaller dimensions, chi equals 2. And what I'm going to assume is this isometry has some exact form. So this exact form looks like this. Okay. Where this guy, so this guy is 1 over square root 2 of, say, up, down, minus down, up. You just do that for this guy. Okay, so this whole thing is my isometry where so I'm just interpreting these lines as just two-side identity, like a straight line is just an identity. Okay, so we just have some very simple isometry that just permutes these two lines, combines two of the inputs into a single. And you can check if I take this W with this conjugate, I just get out, so W dagger equals, actually the other way around, just equals the identity on this chi equals 4. Okay. Similarly, I'm going to take a unitary, a disentangler, and it's going to look like this, where okay, so again, let's draw an outline around this just to make it simpler. So again, it's just a mapping between this bond dimension 4 and bond dimension 4 based on these simple permutations. So now I'm going to ask the question, what happens if I'm going to build a binary MERA? So a 2-to-1 scheme based on these guys. Okay, so just draw a little bit of it. Okay, so forth. What sort of state do we get when we put these tensors here? Let's have a look. So let's imagine, so each of these indices down here is some double index, if you like, that connects to, I can think of as a product of two sites. Let's sort of follow what happens, follow along one of these lines. So imagine I start on this side, so the outside of this leg, and this disentangler, I cross over again, going out, I cross over, I come into this isometry. I think I've done that right. Yes. I cross over, go around, I cross over, go down, and I follow it out. Okay, so I'm just, it's much easier if you draw in all of this fine detail of these tensors. You can just see if I start on a line here, or I follow it up to a line here. Similarly, if I start on a line here, I follow it out. Okay, so I see I have these singlets. So each of these describes a singlet of entanglement. I have, if this is an n-site lattice, I have n over 2 of them at distance 4 sites. Okay, let's look at what happens if I follow one here. I go around, I go up, I go around, I go around, I go through, I go around, I go through. So I should be doing this more carefully, but I think this is correct. And again, I can, each time I go across a wire, I'm just crossing over. Each time I go through a disentangler, I'm crossing over, following this rule. And if I look at this, I get a bunch more singlets. I have n over 4 of them. I think at roughly distance 8 sites apart. And when I look at these, I'll have a whole bunch more that go like this, so forth. I will have n over 8 that are roughly distance 16 sites. So I'll have ones that go all the way over there and back. So the state I've described with this simple choice of tensors is just this complicated product of singlets where I have singlets at all different length scales, all sort of mixed in with one another. What you can see when you look at this in a little more detail is that if I look at a block of L sites, no matter where I choose the L, there will be roughly log L entanglement. So some sites may differ by some constant factors, or some sites may have slightly more or slightly less, but it will be roughly log L of these singlets will always terminate on some block of sites. Okay. So clearly in this very simple example we concocted, the scaling of entanglement entropy in all blocks goes as the logarithmic correction. And what we can see is that, so this is MERA with bond dimension chi equals 4. Imagine this lattice was infinitely big. I still have this MERA bond dimension chi equals 4. If I asked you, could you represent the state with the matrix product state, you would need matrix product state chi equals infinity. So you'd have infinite, across any left-right partition, you'd have infinitely many singlets across, so you'd need infinitely many bond dimension. So I think this is a nice illustration of how MERA can represent log L entanglement, why in some cases it's more powerful than matrix product states. This doesn't look like the ground state of a critical system, but I like to think of a critical system as some kind of translational invariant mixture of this. It has this has the same scaling entanglement as I expect from a critical system. So let me just finish very quickly. So just some. Okay, so prospects. So I think 1D MERA is very good. The calculation, the computational cost we've sort of got under control, works pretty well. You can study potentially some quite interesting things with that. 2D MERA is conceptually very nice, so all of the formalism I showed you today carries over to the higher dimension, but it's very expensive computationally. This is something we're still struggling with. It's very, very just difficult to do. There is progress being made in many directions to make this more manageable. So some of this is, for instance, this tensor network renormalization that I didn't get to talk about. Some of this is progress to doing MERA more efficiently, and sort of the generalization, putting MERA in this framework of path integrals or partition functions, and you can do things better than you can on this sort of lattice formalism. We will also learn from We'll also learn from Tadashi Takeyanagi about the continuous MERA. So the version of this sort of invented by Frank Fistrata, where you no longer have a lattice, you're describing a field theory using similar ideas. And a lot of people are also interested in ADS-CFT and holography. So people are interested, some people think that this MERA is a realization of ADS-CFT correspondence, which is a correspondence between semi-classical gravity and conformal field theories. In particular, that here I have sort of a two-dimensional bulk of tensors, like a space and a scale dimension, that described as CFT on the boundary, that maybe the sort of two-dimensional bulk has something to do with anti-de Sitter space or classical gravity. All right, thanks for your attention. Thank you all.
So many questions already. Maybe everything has been clear.
I have a question. In this example, you define explicitly the structure of disentangler. However, such unitary operator can be understood as a disentangler. Even disentangler is a single of some line. It's not so clear. But why it is a disentangler? Of course, it's a unitary operator, but how to disentangle anything?
I think it's a little bit clear. So I have some state that has two singlets. Well, I know it has a singlet here, one here. Okay, so this is some block I'm dealing with. Now notice my block has a singlet between a site inside and a site outside. After I do the disentangling, I've moved, so this spin is entangled with one over here. This disentangler just shifts the spin that's entangled to outside and shifts Yeah, I mean, it's really just, there is a spin in the block that's entangled with something else. It just shifts it outside just by doing some permutation. So it's some very primitive disentangler.
Ah, I see. Thank you.
How do you choose the disentanglement for given models?
For a given model, we can just do the same sort of variational calculation, just choose all of the tensors to minimize the energy. So for a given Hamiltonian, you just treat this as a tensor network ansatz. So all of these tensors contain variational parameters. I just want to choose the parameters to minimize the energy of this state. So you're not actually, people have tried, for instance, to choose the unitary to minimize the entanglement across the cut in some way, or that never seems to work. We don't have any, in general, we don't have any intuition for how to build disentangles apart from whatever does the best job of minimizing the energy. There's no more insight in that. Apart from like specific examples you can give. So yeah, I think that there is a lot to be understood with MERA, that like numerically it works very well. Conceptually, you have many questions that illustrated sort of things we don't understand that could be done much nicer. So please solve these problems for us.
Okay. If there is no further question, let's thank the lecturer again.